Hello guys, in this video we will talk about how computations work in neural network. So I will talk about the entire math involved in one forward pass or one forward propagation of a neural network. Okay, so we have already seen a general neural network architecture, so we will stick to the same architecture in order to explain computation. Okay, so you all know that the number of neurons in the input layer will be equal to the number of features that we have in our data set. Okay, that's one thing which you have to remember. Now, before actually jumping into computation on the neural networks part, let us first try to understand logistic regression as a neural network. Okay, so this will ease up the things in order to understand the computations further in a neural network. Okay, so let's say, understanding logistic regression in terms of neural networks. Okay, so let's see how it does. So let's say we have only one example, one training example, and with three features. So how logistic regression works is we have x1, x2, x3. So these are our features, correct? In one training example, we have three features and these are the three features. So what I will do, I will draw a neuron here. I will connect the inputs to this particular neuron here. Okay. Now, in order to do a logistic regression, what we did theta transpose x and applied sigmoid function to that, right? And how it looks like, it 1 by 1 plus e to the power minus theta transpose x, right? So this is what logistic regression is actually. So in order to understand with respect to a neurons, so what I'll do, I will divide this neuron into two parts just for the sake of understanding. Okay, and to explain the two functionalities of this particular neuron. So first, what it will do, it will compute this theta transpose x. So in case of neural networks, let's call thetas as our weights and represent them as w's. So this will have w1 associated with it, w2 and w3. Okay, w1 is associated with first feature, w2 will be associated with second feature, w3 will be associated with third feature. What will happen? It will be w transpose x. Okay, and this will apply, let's call this w transpose x as small z, and in the second part of this computation it will apply the sigmoid function to this particular z, and before applying sigmoid function it will also add the bias. So this is called as bias. So what happened here? So we have our w, which is w1, w2, w3. It's of shape 3 cross 1, and we have our x, which is only a single training example. It's x1, x2, x3. This is of shape 3 cross 1. So what we will do? We will do w transpose x first. Okay. When we transpose it, its shape will be 1 cross 3, and we are multiplying this matrix with, transpose the matrix with a matrix of shape 3 cross 1. So the output will be one single number. That's what this neuron will provide us the output with. Okay, and after doing this w transpose x, we will add the bias term here, and together this we call this as a small z, and we will apply activation to this z, and we call it as a activation. Okay, so the final output after applying sigmoid activation function is called as a activation neuron, the value of after applying the activation, right? So just know that sigmoid is one of the activation functions that we will be using in neural networks. So hope this is clear. If you have understood this, the next part will be very easy. Okay. Now, so just let me quickly refresh our neural network architecture that we are considering. We will be considering three neurons in the input layer, and as we are assuming we will have only three features. We have one hidden layer with 4 neurons in it. So the size of this hidden layer is 4, and in output layer we will have one neuron. The size of the output layer will be 1, and similarly the size of the input layer is 3. Okay. Now I told you each layer will have the weights associated with it, which are learnable. The transition from input to hidden layers is governed by a weight matrix called as W1. Thus, this one indicates that the weights are associated with layer 1, the hidden layer. Okay. Similarly, the transition from hidden layer to the output layer is monitored or governed with the help of another set of weights. We denote it as W2. Okay. And each layer, hidden and output layer, will have their own bias B1 and B2. Okay. So this is just a quick recap. Now, this is how the weight matrix looks like. At layer 1, the shape will be 4 cross 3, and at layer 2, the weight matrix will be of shape 1 cross 4. So this is how it looks like. And our data, we have stacked all the training example horizontally and call that as capital X, and it will be of shape N cross M. Okay. Now what we need to do, let's just take a single example. Now guys, listen carefully, it's very important. Now I'm actually explaining a forward pass steps in a neural network, okay, or forward propagation steps. You can call it by whatever name you want. Now let's take one training example for our understanding, and we will multiply that training example with the weights matrix, right? So in order to do that, what we'll do, we do not need to do the transpose of the matrix because the weight size of the matrix and the size of the single training example are already compatible here. Just the representation is changed with respect to X, so it is compatible already. Why I am saying it's compatible? Let's try to understand. Weight is of shape, weight matrix is of shape 4 cross 3 for the first layer, and the first input example will be of shape 3 cross 1 because we have 3 features, right? So now, in order to have the matrix multiplication, these are our shapes, right? 4 cross 3, 3 cross 1. So the basic condition is matching for matrix multiplication. So we can multiply directly without using transpose of the matrix. So the resulting output will be of shape 4 cross 1. So for one training example, we will calculate the values for each of these neurons, right? And whatever we did here, W into X1, right? W of 1 into X1 is just the first part of first neuron in the hidden layer. So just like this. So this is the first part, right? So we just did this one here. And how the computation looks like, you just multiply, you just do the matrix multiplication, guys. So W11 into X1, W12 into X2 plus W13 into X3, right? So this will be our first value. Then W21 into X1 plus W22 into X2 plus W23 into X3. So like this, we will go till the fourth row of the weight matrix. W41 into X1 plus W42 into X2 plus W43 into X3, right? Once we have these numbers, we will add a bias number to this particular matrix, right? So this is how it works. So let's say now we have arrived at, we call it as Z, right? Z1, Z2, Z3, Z4, or before calling it Z, let's just call it some unknown numbers, okay? So let's just call it as num1, num2, num3 and num4, okay? And then we are adding a bias term to that, and it will be a single number num. So how this will happen? This number will be added to these individual numbers in this particular matrix or vector of size 4 cross 1, right? And how it does internally in Python, this will be broadcasted into the same shape as we have the target matrix, right? So this one number will be converted or broadcasted 4 times, num, 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 num. So this is called as Python broadcasting. Python broadcasting. Okay. So once we add this bias, we will call this as Z. Here, if you remember, in case of logistic regression, we called this as Z, small z, after adding the bias. So similarly, we will call this as Z. Since we have 4 numbers associated with it, we will number it. Small z, first layer, first training example, okay, first unit. Second unit of Z, in the first layer of the first training example. Third unit of z in the first layer of the first training example. Fourth unit of z in the first layer of the first training example. This should be one first training example. Okay. Together this we can represent it as z11. So this represents the layer number, and this represents the training example number. Since we are considering the first training example, I am representing it as 1, and it will be of shape 4 cross 1. Now once this is done, we will apply the activation functions. Before doing that, let me tell you one thing. We do this, we compute these z's for all the training examples that we have in our matrix capital X, right? So then what we do, we stack these z's horizontally, right? So we will get a big matrix like this: z1 1, right? z12, z1m, right? We will stack that horizontally. Then what we will do, we will apply some activation functions for all of these z's, right? And in case of sigmoid function or logistic regression, this will be sigmoid activation function, right? After applying the activation functions, we call them as A's, right? So applying activation function for z, first unit of z at the first layer for the first example, we will get A11 of 1, A2 of 1, 1, A3 of 1, 1, A4 of 1, 1. So you might be wondering what are these A's. I have represented that in this particular neural network architecture. So this A is after applying the activation function to that particular unit Z. Okay. So this is the activation function for, now we have calculated for only one training example. So like this we will compute for all the M training examples. Once we have that, we will stack again all these activation functions horizontally, and this will be of shape 4 cross M, right? Because we have 4 z's, right, small z's for each training example, and like this we have M training examples, right? So this, nothing changes here. This will remain 4, this will remain M number of training examples. So what we will do, we will apply activation function for each of these small z's, and we will get A values, right? So these 4 will remain 4, and these M columns will remain M columns. So again the activations will also be of shape 4 cross M. Why 4 cross M? Because we have 4 activation neurons in the hidden layer. So that's why it will be 4 cross M. If you are not understanding, please rewind and watch it. It's really easy. Once you understand it, it will be very easy to play around with the neural networks. Okay. So once you have this, we will stack again for all the training examples. We will stack the activation values horizontally and call this as a capital A of 1. This 1 again, remember, it represents the layer number. So if we have the subscript with the small brackets or the round brackets, this will represent the training example number. The numbers inside the square bracket will represent the layer number. Okay, do not get confused with that. Now I have told we'll apply activation functions, right? So usually these activation functions will be non-linear. So you have seen theta transpose x in case of linear regression. This is a linear transformation, right? And in case of logistic regression, we are applying sigmoid function, which is a non-linear transformation, right? So in case of neural networks, we mostly 99% of the times we will end up applying non-linear activation functions in the hidden layers and the output layers. Unless we want it to be linear, we do not apply it. Most probably it will be non-linear activation functions. And there are many activation functions. One example you already know is of sigmoid function or logistic function. Another is called as ReLU. It is rectified linear unit, right? ReLU stands for rectified linear unit. There is something called as TANH. There is also something called as leaky ReLU, right? So there are many more. I'll explain on the activation functions in a separate video. Let's not worry about this. Okay. So right now we have seen how do we calculate activations for each training example, right? So in order to do this, we'll have to run multiple for loops, right? First, we have to run a for loop on the number of training examples that we have, right? That is M. Usually, when it comes to neural network, the training data set will be huge. It will be in 100,000, 200,000 or millions, 10 millions of records, okay? So, we have to run that big for loop, and inside that, we have to run multiple for loops to compute these matrix multiplication values, and then in the end, for each of those values, we will have to apply the activation functions. So this will not be efficient when it comes to time consumption. It will take a lot of time. So how do we speed it up? So we speed it up using a concept called as vectorization. Okay. And this I have explained in my another video earlier with the name how to avoid for loops. How to avoid for loops. And instead of for loops, we can make use of matrix multiplication, right? So you might be wondering, while I was explaining calculation of small z and calculation of activations, I am repeatedly telling to stack the values of all the training examples horizontally to obtain a matrix of shape 4 cross m, right? So that is for the purpose of vectorization, right? Now we will see how we can in one shot learn these z's with the help of matrix multiplication, and how in the same way how we can learn the activations. So let's see that. We know that our weight matrix at the first layer is of shape 4 cross 3, correct? And we have our capital X, which is the collection of entire training example, which is of shape n cross m, and in our case n is 3, so it will be 3 cross m, right? Now what we will do? We will make use of this weight matrix and this X as a whole and do the multiplication. Can we do the multiplication? Yes, we can do the multiplication. Why? Because the shapes match, the condition or the criteria matches to perform the matrix multiplication here. So this 3 and it's 3 here, and the resulting output will be 4 cross m, which we have seen earlier after stacking the entire training examples horizontally, right? So what we get? We get W11 into X11 plus W12 into X12 plus W13 into X13. So this is for first training example. Then we will go W11 into X1 of 2, W12 into X2 of 2 plus W13 of X3 of 2. So this is first training example, this is second training example. Like this we have mth training example, right? So we will go on computing the required z's in case of this matrix multiplication for the entire data set that we have in one shot without using any for loops. Okay. Once we have this output, which will be of shape 4 by m, we will add the bias associated with that particular layer, which we represent it as B1. So this layer will have a bias, right? So you can see that in this architecture. So this will have a bias B1. The output layer will have the bias B2, and both these will be a single number. Both are different, but it will be a single number. So hope this is clear how we are speeding up the process using matrix multiplication. We call it as vectorization. So once we have this, we call this as capital Z. Okay. Once we have this capital Z, right, this is how the matrix multiplication and its output looks like. So here I have written the matrix multiplication for 2 training examples, and in the end I have written for the mth training example, right? So W11 into X11 plus W12 into X12 plus W13 into X13. So this is the first number. Then we will go to the next column in the second matrix, that is X. W11 into X12, W12 into X22, W13 into X32. So this is how the computation goes. This is a simple matrix multiplication. There is no rocket science in this, right? So if you understand the matrix multiplication, you will get to know what I have written here. Okay. and then we will add the bias. We call this entire matrix after adding the bias as capital Z, and since it is computed at first layer, we will represent it at Z of 1 under the square bracket. So this represents the layer number, and it will be of shape 4 cross M. Now that we have Z, we have computed the first part in this neuron, or you can refer this architecture. We have computed the first part, that is the computing Z part for all the input training example. Okay. Now that we have computed Z, we will apply activation function on top of this Z, and we call that resulting matrix as A of 1. So this again 1 represents the layer number, and this A is the activation matrix, and since it's just the layer 1, we are calculating it at layer 1, we will represent it as A1. Hope it's clear, guys. Now we have completed the calculation of activations or the final result with respect to all these neurons in the hidden layer or layer 1. Now we will see how we calculate the output of this particular layer, that is layer 2 or the last layer in our example neural network. So if you can think of it, the input to this particular layer 2 will be activations from the previous layer, that's layer 1. So we take matrix A as input to our last layer as our input, right? Output from the previous layer will be input to the next layer in the neural network. So it's in general we can say that. So let's say we have multiple layers associated in a neural network. So in our case we have taken only one hidden and one output layer. So generally it can have multiple layers. So this is input, this is hidden layer 1, hidden layer 2, hidden layer 3, and this is output layer, and we call it as layer 4. So the input for hidden layer 1 is the output of the previous layer, right? The input for layer 2 will be the output from the layer 1, correct? Similarly, the input for layer 3 will be the output of layer 2. And in the end, the input for layer 4 will be the output from previous layer, that is layer 3. So this is how the general input works in case of neural network. Okay. So now let's understand how the output is computed. So as I told you, input for the layer 2 in our case will be activations from the previous layer, and we denoted it as A of 1, right? We are calculating the output for layer 2 now. So the input for this layer calculation will be from layer 1, and what those inputs will be? It will be activation functions which are associated with that particular layer, layer 1, right? And again, this A is of shape 4 cross M, right? And the weights which are governing the transition from hidden layer or layer 1 to layer 2 is W2, which is of shape 1 cross 4. So you can see it here, 1 cross 4, right? So the weights, I'll just write the weights here. Weights 2 is of shape 1 cross 4. And what are these weights? 1, 1, 1, 1, 2, W1, 3, W1, 4. And these are associated with layer 2. Okay. This might seem a bit tricky, complex, but it's not complex. All it is doing is just applying matrix multiplication and in the end adding a bias to that. And on top of that, we will apply some activation functions to convert it into non-linear form, right? So that's it. It's nothing much in this. So what we'll do, we will again do the same thing. For the computation of the first layer, we did W1 into X. For the computation of the second layer, we will do A2. This will be acting as our X, and we will multiply the weights with this, right? So how it will do? It will be of shape 1 cross 4, and this will be A1, sorry, this will be A1. A1 will be of shape 4 cross M. The resulting output will be 1 cross M, right? So it will have one row and multiple predictions. So predictions will be represented by Y hat. It will have M predictions. Why M predictions? Because we have M training example, we will have M target values, right? So that's how the forward pass, one forward pass in a neural network works. So if you have multiple layers like this, you can always consider. So let me just quickly tell that as well. It won't take much time. So let's take this as our input or layer 0. This is our hidden layer with 3 neurons, layer 1. This is another hidden layer with 2 neurons, layer 2, and finally output layer called as layer 3 with 1 neuron. Okay. So the size of the activation function for the layer 1 will be, it will be denoted as A1, right? It will be similar to what we have here. So A1 is of size 4 cross M in our case. In our general architecture, it will be 3 because we have 3 neurons. It will be 3 cross M. Okay, and this activations at layer 2 will be of shape 2 cross M because we have 2 neurons, and this output will be of shape 1 cross M finally, right? And what will the weight matrix with respect to this? It will be 3 cross 4. This weight W2 will be 2 cross 3, right? And W3, it will be 1 cross 2. So this is how the weights look like, the weight matrix looks like. So in order to compute the activations for L2, or just consider the input for L2, what will be the input for L2? It will be A1, activations from layer 1, right? And what's the weight matrix that is governing the transition? That is W2. Now if you take the shape of A1, it is 3 comma M. Shape of W2, it will be 2 comma 3. So what we will do, we will multiply W with A1, W2 with A1. It's of shape 2 comma 3. This is of shape 3 comma M. So output will be 2 comma M, which will be our activation layer 2, activations at layer 2. So this is how a one forward pass, we call this as forward pass, and this is just happened once in our explanation. This is one forward pass, or in general you can call it as forward pass or forward propagation. Okay. So this is how the neural network's forward propagation works. So I try to explain it in simple way, as simple as possible. If you have any questions or if you think that it's complex, let me know. I'll try to simplify it once more and then release another video. Okay. So that's it for this, guys. So if you haven't subscribed to my channel, please do subscribe. I'll be releasing many more videos on neural networks in upcoming days. So stay tuned till we meet in the next video. Happy learning. Bye bye.